Hello, I'm Rafał. I came from Poland, and I'm super happy to be here. And I will tell you about caching, especially about caching in the microservice world. Before we begin, a few words about myself. So I'm a cloud software engineer at Hazelcast. I used to work before at Google and at CERN, so I spent some of my life, almost 2 years, in Switzerland, but I've never been to Lugano. It's very nice here, really. I'm also an author of the book Continuous Delivery with Docker and Jenkins, and from time to time I do conference speaking and trainings, but I'm an engineer in general. A few words about Hazelcast. So Hazelcast is a distributed company. It's a distributed company in two meanings. First is distributed because we produce distributed open source software. But the second thing is that we all work this remotely. I work from Poland, but there are people from all over the world. We have three products. First one is Hazelcast AMDG. So if you hear about Hazelcast, that's probably the first one. But we also have a Hazelcast Jet, which is a library for stream processing. And we have a brand new product, which is Hazelcast Cloud, which is basically Hazelcast as a service. Our agenda for today is super simple. So there will be a very short introduction about caching in general, and then we will walk through all the possible caching patterns that you can use in your microservice system. I would like you to think about two things while you're looking at this presentation. First thing is, which one of this architecture do I use in my system? Because this list is complete, so you must use one of them. And the second question is, can I change? Does it make sense to change to any other for my system? So let's start. Why do we do caching? You will see caching in every system. We do it basically for two reasons. One is the most obvious, is the performance. So we would like to have things faster. We don't want to do some long-lasting, time-consuming, like processing or calling some external services twice. So we cache the value. Second one is resilience. It's maybe less obvious, but still, like your system or part of your system can be down. But if you have your value cached, maybe the customer will not even realize. It depends what your system is doing. But if you, for example, serve recommendations on Amazon, if the service for recommendation is down, you may maybe return the old recommendation and user will not even realize. How does caching fit into the microservice world? So this is a classic microservice system. So we have services. Services can have versions. They are written in different programming languages. They can use each other. So the question is, where do we put cache on this diagram? Should it go like inside the service, or as a separate entity, as a separate cache server, or maybe in front of the services? And that is what this talk will be about. So the first option you have is to use embedded cache. That's the simplest option possible. The idea is like this. A request comes to your system, goes to load balancer. Load balancer forwards it to one of your application web services. And inside this application service, you have cache deployed together with your application. So application checks if I already processed such kind of data by querying the cache. If yes, then return the value from cache. If no, do some long time-consuming business logic and put it into cache and return the result. This time-consuming business logic can be anything like calling external service or call to the database or whatever, or some long-time calculation, whatever takes time. Now it's so simple that if you can even try to write it yourself. Like if you like Java, that would be something like this. You can have concurrent hash map. we process the request, check it if the cache already contains the request. If yes, return the cached value. If no, do some processing, put it into cache, and return the response. You can do it, but yeah, please don't, because Java collection is not a cache. It's not a cache because it has no eviction policies, no max size limit, no statistics, no built-in cache loaders, no expiration time, no notification mechanism. So it's not a good idea. But still, you can use something. No, if you don't write it yourself, you use, for example, Guava cache is a very good solution. You specify all these parameters that are missing from the concurrent hash map in your constructor or builder here, and perfect cache. Another solution is EH cache. We can even put like the caching layer one abstraction level higher and put it into our framework like Spring, and you don't even have to write all over again the same logic for caching. So if you use Spring, you annotate your method cacheable, and then every call to this method will first check if ISBN was already stored in the cache. If yes, return the cache value. If no, do execute find book and slow source method. But be careful, because Spring uses concurrent hash map by default for some reason. So you're better off by defining your cache manager, for example, as Guava. So back to our diagram. So this is the simplest idea. That was an example for Java, but in any programming language you will find a library to do simple caching. One of the problems we have here is that imagine that your first request goes to the service at the top. It gets cached, everything is fine. However, if the same request goes to the application at the bottom, we have to do this processing again, because these caches are completely separated. They are run together with JVM or a program. So one improvement to the embedded cache would be to use embedded distributed cache. It is still the same pattern, it's still embedded, but it's some kind of improvement. This time you can use different library. I will talk about Hazelcast because that's the easiest for me, because I'm from Hazelcast. But you can use some other libraries, I guess, for other languages. Hazelcast is for Java, but you can use for other languages some other libraries. So this time the story is the same, but no matter which application web service is caching the value, they use the same cache. So the caches in each application form one caching cluster. How to use it if we stick to the example from Spring, all you have to do is to define Hazelcast library as your cache manager, and then everything will happen in a distributed manner. So a quick demo, I will start two applications, like Spring Boot application, and caches will form one cluster. So the configuration is exactly the same, what you've seen on the slide. So all we defined was the cache manager. Now if we run it in two instances of the same service, which is what you usually do, have multiple replicas of the same service, then you will see that they form one cluster. So this is the first application. Started the cluster with one member, and then if we look at the second application, it should join the cluster, and the cache is together. You may wonder how it's possible that the cache is forming cluster together. How do they find themselves? So locally they use multicast. That's the easy way. However, what we thought is a good idea is to provide a plugin for each environment. So if you use Kubernetes, you just plug in the Kubernetes environment, and then the caches will use Kubernetes API to discover themselves. The same for AWS, for Azure, for GCP. So if you don't use any of these environments, there are more. There's for Docker Swarm from the community plugin. But if you don't use any of those, you can still run a Eureka server or Zookeeper and use like a Eureka service registry as a registry for Hazelcast to discover themselves. We actually do like a lot of blogging of how to set it up. So if you're interested in details, just go to our blog page. So that's about embedded cache. Let's look at on the pros and cons of using embedded cache. So good thing is that the configuration was super simple. It goes together with your application. You don't need any like ops effort or ops team to manage the cache. Low latency, you cannot do anything better than to have cache inside your web service. So in Java, inside the same JVM, you will not make better latency than that. From the downsides, the management is not flexible. So imagine that you have a peak load of your service and you receive too many entries to the cache. How do you scale it up? You have to scale it up together with your application. It's limited to only JVM based or your language of choice. And data is collocated with application, which may not seem like a big issue, but usually for big customers or for big organization, that is a problem, that you store the data where your application replica is at the same machine. That's about embedded cache. So the next pattern is client server. So now we take this caching part outside the services. So the flow looks as follows. Again, the request comes to the load balancer. It goes to the one of the application web services. And application has to check it in the cache, but this time it uses cache client to connect to cache server, which is deployed somewhere, like a separate unit in our system. It's kind of a database style, like your cache is a separate thing in your system. So if we compare it to the embedded mode, what is different? Like there are two main differences. So one is now we have this thing, so we have to take care of this, which is good and bad. Good is that we can manage it separately, scale it up, scale it down. But the bad thing is we have to take care of this, like to have an ops team or developers can do it, but it requires some effort. But the second difference is here. So now the application uses a client to connect to the cache, which may not sound like a big thing. However, it is, because now we use like a well-defined protocol. So the client library can be in any programming language, which is usually the case. Like you have a cache cluster and a lot of applications written in different programming languages, and they all connect to the caching cluster. This time you are not limited to the Hazelcast, but you can use like different solutions like Redis. Probably most people in the web world now uses Redis. So Redis, that's actually the Redis you can use only in this pattern, like client server, because it's written, I guess, in C, so you cannot embed it in your Java application. So the only deployment pattern for this is like to use the client server. Or if you work in some older project, you may want to use Memcached, which is not so popular in new projects. How to set up the server? So I will stick again to the Hazelcast example, not because of advertising this, but it's just the simplest way for me to show it because I work day to day with Hazelcast. So if you use like an on-premise version, you just use the one script, start as H. The discovery strategies, it will help you form the cluster on whatever environment is deployed. If you are doing like Kubernetes deployment, like most people on Greenfield project now, then we provide it as a Helm chart. Helm chart is a package manager in the Kubernetes world. So with this one command, you will have all the clusters with multiple replica already deployed in Kubernetes. How does like client looks like? This is the Spring configuration that will make your client connect to the cluster if you are using Kubernetes. So again, we use this Kubernetes config, which uses Kubernetes plugin, and it will discover the cluster by itself. So coming back to our diagram. So we have this thing that we have to do with our cluster. So if you don't want to do it, but you would still like to use kind of client server, we can move these ops activities to outside of our organization, move it into cloud. Like everyone is going into cloud, so that's like when we discuss with customers, everyone is doing this. Like big customers, like even if they don't have to, they do it because it's a trend now. So how does it look like with the cloud version? So we provide Hazelcast Cloud, but in most caching providers, Redis has their own Redis labs. The idea is exactly the same. The architecture is like client server, but you just don't have to do all this activities because you pay someone to do it for you. As I said, like all the process is the same as client server. It uses the cache client to connect and so on. How the configuration would look like? So that is the configuration if you use Hazelcast Cloud. So you say, okay, use the cloud config. You put a discovery token, so how to find your cluster, to cache cluster in the cloud. You put your cluster name and the password for it, and that's all. So a very short demo how it looks like if you would like to start with Hazelcast Cloud. So if you go to cloud hazelcast.com, you will see a web console like on every cloud product now. You click on create cluster, then give a cluster name. You can use it for free for small clusters, as I did here, and you select the underlying cloud provider, the region, other parameters, and start the cluster. This selecting the underlying cloud provider and the region is very important, and this I will explain in a second. Why it is like the critical. Then you click on the configuration, grab the parameters like discovery token and the password. Put it into your Spring application or configuration, and then when you start the application, it will connect to this cluster. So as simple as that. If you use any like cloud thing like databases, MongoDB or whatever, the process is more or less the same. You have like some discovery token, you don't put any URLs, and it's automatically discovered. So when we run it, you will see that the same application will this time not create the embedded cache, but connect to this cache which is in the cloud. You have to trust me or just see that this IP is actually a public IP. So the pros and cons of client server and cloud cache. So the good thing is that data is separated from the application, which is a must usually for big organizations. We have separate management, so scaling, backups, everything is like separately. And it's programming language agnostic, so use whatever programming language you want, as long as you have a library for this, but if you don't, you can always write your own. From the downsides, like it requires some effort, or you have to pay to have it in the cloud. The latency is higher, and that is like, I told you a moment before that it was important to select in the cloud, to select the underlying cloud provider and the region. Because like, if you go with your caching to the cloud, your application, like your services, have to be deployed on the same cloud provider as the cache. Because like, it doesn't make sense to run, like I did, like run application on my laptop and go to the cloud in the US, because it would be just too slow. So we are in the area of in-memory computing. Cache is all the area of in-memory computing, which has requirements like even higher, even like more limited than databases. So latency has to be really, really small. Like even like one hop over the network, over the router is a big thing. So if you deploy it on a premise, you have to deploy it on the same local network than your applications. If you deploy it on the cloud, then use the same cloud provider, the same region, and even what we do is like we do a VPC peering. So you really peer the same VPC network. So that it's really the same, even though it's like the same network for in the cloud. That is like that's why one of the challenges while building like our Hazelcast cloud, that you have to provide all these functionalities, because otherwise it would be too slow for people. Cache must have very, very low latency, like 100 milliseconds is already like too high. So we did like a client server and a cloud. Now let's have some more fun. So these two first architectural patterns, like embedded and client server, that were kind of easy or old known. This one, Sidecar, is something completely new. So this time this diagram is specific to Kubernetes, because the Sidecar pattern is limited to the containers, containerized environments, mostly seen nowadays in Kubernetes, so I limited this to Kubernetes. So a few words about Kubernetes. If you didn't hear about Kubernetes, so just a few sentences just to clarify it. So in the Kubernetes, a deployment unit is called a pod. And this pod usually contains one container with your application. However, you may have some additional containers in the same pod. One pod is always deployed on one physical machine. That is important. And these additional containers, it can be, for example, a logging agent that will take your logs from your application and send it somewhere. That is a very good example of this additional container. This additional container can be also a cache, like on this diagram. And this additional container is called a sidecar container. That's why this pattern is called sidecar pattern. So how does it look like? So again, request goes to our system. It goes to the Kubernetes service, which is kind of a load balancer in the Kubernetes world. Then it goes to one of the pods. Application receives the request. It uses cache client to connect to the cache server, but this cache server is always located on the same physical machine. And the rest is as on the other diagrams. So this solution is kind of somewhere like in between, like embedded mode and client server mode. You may think of this as embedded mode because it's always deployed on the cache is always deployed on the same physical machine. It's not the same JVM process, but it's the same machine. It uses the same resource pool, so it scales up, down together with your application, and you don't need any discovery because it's always local host. However, you may also think like it's a client server because we can use different programming languages. Because after all, you use cache client to connect to the cache server, and there is some isolation between application data and cache. This isolation is not on the machine level, but is on the container level. How would the code look like? Again, the same example. So we configure the client. We set up the static address as a configuration, but this static address, this is not a problem, this is static because it's always localhost. It will not change. How would the Kubernetes configuration look like? So we define a deployment with a template for the pod, and in this pod we have two containers. One is our application containers, which is business logic. It will be always different. And the second one is like a Hazelcast, so it will be always the same. This will be this cache. And obviously, as you see on the diagram, like different like pods, this caching part, they form one cluster. So we are still like in the distributed environment. What is good, what is bad? Like simple configuration again. Programming language agnostic, low latency because we are on the same machine. There is some isolation of data and applications. From the downsides, it's limited to container-based environment. The management is again not flexible because it will scale, again, if you think like it will scale up and down together with your application. And technically, data is collocated in the same application pod. So this data and cache data in the application, there is some isolation, but it's not, after all, it's not, so it may be enough or not, depending on your like security requirements. Now there will be something slightly different. So far, all these patterns, in all these patterns, like application was aware that it uses cache. Either it uses some embedded thing or client, but it was aware that it should take a request and ask cache if the data is cached. This time it will be different. The cache will be in front of the application. So a request comes to the application, comes to the load balancer, and just before or just after the load balancer, we have the cache, which caches on the protocol level. Like in this example, you can use Nginx, and it will cache on the HTTP level. If such request was already executed, return the cached response. If no, go to the application. So it's like completely different approach. You can use Nginx for this. In your Nginx configuration, all you have to define is like the place on the disk where to store the data. You can obviously configure much more like how long is the timeout and so on. But that would be the most basic configuration. Nginx is good because it's very stable. It's used everywhere, so it's like something you can use on production. But it has some downsides, like it's only for HTTP, which is not a big thing. It's not distributed, which is a big thing. It's not highly available, and data is stored on a disk, which is a big thing actually, because if you think about it, all we had before, the data was in memory. And actually, like this, again, we are in the area of in-memory data computing, where the requirements of the latency are very strict. So you usually don't want to have your data stored on a disk because it's slow. Nginx has some you can actually, it has a plug-in mechanism when you can plug in your cache provider. However, like for Hazelcast, it doesn't exist, so you cannot use it. For Redis, it exists, but it's not super mature. Maybe they will make it better, then you can use it. For now, it's not yet even the version 1.0, so maybe for testing, but not necessarily for production. Now, we can take this pattern, this proxy pattern, and combine it with the sidecar. That would be our the last pattern, like the last final thing we will see today. So again, like we are with the sidecar, we will limit ourselves to the Kubernetes environment, and it works as follows. So request goes to the Kubernetes service, then it's load balanced to one of the Kubernetes pods, but this time it does not go to the application container, but it goes to this reverse proxy cache container, and only if it does not have the cached value, it goes to the application. So such idea that application is not aware of the cache, so it has some good and bad sides. You may already guessed, like it's good or bad. Let's start from the good things. So coming back to the diagram from beginning of this presentation. So classic microservice system, like different programming languages, different versions, services using each other. Now, if you think about it, like now if you'd like to introduce a cache, you don't even have to change any code of the application, even build it again. Now, in a declarative manner, you can say, I would like this and this service to be cached. And that's like a big thing, because like you don't introduce some bugs, you know. Changing code is always like a kind of worst thing. So this is very, very like nice that you can specify in declarative in a configuration that, yes, I would like this and this, please provide a cache for me. How do it look like in Kubernetes? So Kubernetes will actually have two containers and one init container. While like this, like let's start from the bottom this time. Bottom is the same, our application with some business logic. Then we have this caching proxy with this cache, this reverse proxy container. We also need some init container for the networking, because by default the request on a given port will go to the application. So we need to change like a IP table of the pod, so that the default, like all the requests from outside of the external request would go to the caching proxy container, not the application. That's why we need some init networking. If you look at this diagram, and this idea that you kind of inject the caching into your system, it may look similar to you like service mesh, Istio, other like super popular topic at the moment. This diagram may look like a diagram from Istio actually, and you would be right, because like the idea is exactly the same. And what Istio wants to do, they actually want to implement caching. They have even like an open ticket like this, but it's not only open ticket. They are really actively working on the implementation, so that you could enable this in a declarative manner in Istio, so it would be stored in an envoy proxy, the caching part. Because as for now, in Istio you can do in the declarative manner, like network management, so how the network goes, the security, but you cannot do caching. But it will come. It will be a big topic like soon. But such approach has also some bad sides, as you may guess. So there is like one thing that becomes much more difficult than when the application is not aware that the cache exists. And this thing is like cache invalidation. If you look anywhere on the internet, like what is the biggest problem with caching is, where should I invalidate data? Meaning, how can I know that my data is stale? Like that I should not use the cache, but go to the database directly. And if you use reverse proxy caching, no matter if the Sidecar or just reverse proxy with Nginx, it's becoming more difficult, because if application is aware of the cache, you can do some application logic to say, okay, if this happens, then don't use the cache, just evict the values from the cache. However, if you use reverse proxy, then you are limited to some, HTTP things like ETAGs, timeouts, TTLs, basically like timeouts. Quick summary of the reverse proxy and reverse proxy Sidecar cache. So from the good things, like it's configuration based. So that is the big win here. There is no need to change the application to apply the cache. It's programming language agnostic. It's everything agnostic. That application does not even know about cache. And it's super consistent with the containers world and microservice world, like what is happening right now. There is this trend to move like everything like not inside your application, but to do it in a declarative way. From the downsides, we mentioned cache invalidation, but also there is no major solution for, at least there is a major solution like Nginx for reverse proxy, but there is no major solution for reverse proxy Sidecar. I said Istio is working on that, so that will be a very good solution. We did, like in Hazelcast, like did a proof of concept, but it's more like a proof of concept, not something one should use. And from the downsides, also like, but there's no major solution, but it will come. You will see, like, I think in like a year or two, it will be like, that's the way you do caching. From the downside, it's protocol based, so usually HTTP. So it's usually fine because everybody uses HTTP now. It's not unless you work in with some super restricted area where then you use probably some other protocols, but like protobufs. But otherwise, like in microservices, you usually use HTTP. So we covered all the patterns. So as a just quick summary, I don't want to tell exactly the same what I already told, but as a quick summary, what I propose is like to give you like a quick decision tree, maybe a little simplified, but still valid. So how do you decide like which pattern to use in your system? I would first ask the question like, should my application be aware of the cache? Is it a requirement? Do I need it? If no, do I run it in with containers? If no, reverse proxy with Nginx. If yes, reverse proxy sidecar as soon as it's available, like some major solution. If my application needs to be aware of the cache, then do I have a lot of data or some security requirements, some security restrictions? If no, then should my application be language agnostic, or do I run in containers? If no, just use embedded or embedded distributed. If yes, use Sidecar. But if you have a lot of data, then the last question you have to ask, is my infrastructure for my application, is it cloud? If no, use on-premise client server. If yes, use the cloud version. It's definitely a little simplified, but it may give you the idea in which direction to look for. As the last slide for this presentation, some resources. So the first one is the blog post, how to run Hazelcast as a sidecar container pattern. Second one is this proof of concept of reverse proxy sidecar using Hazelcast. Third one is a very good blog post about caching in general, like good practices with caching. And the last one is a very good presentation, a very good presentation about how Nginx uses like reverse proxy. How can you use it? What are the good sides, bad sides, and how to configure this? So I would like to thank you for having me here. So it was a pleasure, and now time for questions if you have any.
Hi, thank you for the presentation, very interesting. Well, I was curious to understand a few things, but the most interesting for me actually is the Sidecar cache. What about the invalidation? Not sure if you talk about. It seems to me a problem that affects all the other pattern solution. Actually,
you mean like the cache aside, yes?
Yeah, every pattern has this problem. The only one that it seems to me not very affected is the cloud and well, I don't remember the others, but the centralized ones. Thank you.
Yeah, thank you for the question. So yes, because there's another like orthogonal problem to like the caching. Like here, what I mentioned was where to put your cache. But another thing is how to use caching, because you can like read through, write through, or cache aside. And this is another thing which you can use with these patterns. So it's like another question you have to ask yourself while using cache, which I don't cover in this presentation. So if you use cache aside, then you mean like the async notification on the database like change, yes? Yeah. So yeah, you can actually, if you So you can use them with these patterns, maybe not, as you said, with the cloud. Actually, but you can use them even with the cloud, I think, like if the database would be set, like if you're caching, for example, database, then if the database would be like in the same cloud thing, you can make async calls.
Maybe it would be more clear if you know if there are best practices,
Mhm.
the validation way. I mean, the patterns also.
Mhm.
This would be also very interesting.
Yeah. Yeah, there are like so I can maybe point you to a resource how to, because as I said, like it's completely another topic, how you set up the should I cache before the database, or should I cache like asynchronously, like calls from the database, or should I cache when I read from the database? This is another like another like big topic, like to discuss thing, because these are free valued solutions, so that you can just to make it sure, like you can read through. So when you cache when you read from the database, you can write through. So when you write to the database, you cache it, or you can cache aside. So like async. But this is like a different like question to what I you know what I mean. It's like what was the question was about, like you can use all the patterns here, like with this. It's orthogonal problem to solve.
Yeah, okay, thank you. Well, another question may be also interesting about the cloud. I would see that only a few regions in AWS were supported. This is because of the free version of the service, or there will be more if you are a premium user?
That is not because of the free version. It's just that we just started with this. So we started from free regions. I think now there may be, yeah, there will soon be more. It's just, it's not about free version or non-free. It's just we started from free regions, but we will add more.
And the latency will be very slow only if you are. The latency will be slow only if you are. Sorry, we are. The latency will be short only if you are in the same region, the same VPC, and the same cloud provider option.
Yes, but then you also have to think about the region, the provider, the region, and also the VPC peering is like the most like then you really have in the same network your cache and your application. So you have to think about these three things. The VPC peering you can maybe do without this, like if you are fine with having the same region, but you know that there will be more router hops. Maybe you may be fine with that, but usually if your requirements are strict, then you will also have to have, you would like to have the same network, yeah.
The same zone, at least.
Yes, the same availability zone, yes. Yes. Other question?
Even before you say that simple decision table, but maybe one missing element can be the size of Kubernetes cluster. Even that can impact on your, time to sync
What do you mean?
your cache
But what do you mean about Kubernetes cluster?
size,
I like
the POD numbers.
Like the size of the cluster.
Yeah, size of cluster.
Yeah, but I don't think it will impact, because in any of this, like you will have the same, like it can be, any of this can be a different size of the cache. Sure. Yeah, it will not.
Maybe for huge cluster, you can go.
Yeah, I mean, if you have like, I would say like embedded is usually for simpler cases when you don't have to scale up or down, because if you have like really like, if you need like really manage this cluster like scaling up and down, then you should probably go in the cloud or client server. But because you won't like to have like be possible to scale up your Hazelcast cluster without scaling up your application. This is very very common case. Okay, time is over. So that was the last question. Thank you again